Hey everyone, here with part 5 of our probability section, the conditional probability. All right, and we've already seen this conditional probability definition, when we looked at independence, right? So the probability of A occurring, given that B has already occurred, and again, this is the notation with the vertical line that we use, the probability of A given B, is the probability of A intersect B over the probability of B. All right, and again, we saw this, as you'll recall, in the last video when we talked about independence. Okay, why? Because if the conditional probability of A given B is equal to the probability of A, then A and B are independent. So we looked at that and we've done this example. We looked at this example in terms of are these event sets independent, but now if we're actually just looking at the probability of drawing a heart, right? Well, the hearts, that's one out of the four suits. There are 13 cards per suit, so there's a 1/4 chance of drawing a heart. The probability that a red is drawn is 1/2 because half the deck of cards is black, half the deck of cards is red. And the probability that you draw either a heart or a red card, well, all the hearts are red, so it's 13 out of 52 or 1/4. And using the conditional probability formula, the probability of H given R is the probability of H intersect R, which is 1/4, right? So we take the 1/4 from here and substitute it right here. And then the probability of R is 1/2, so we do that. We invert and multiply, and we get 1/2. Which makes sense. If we know that we've drawn a red card and half the red cards are diamonds and half the red cards are hearts, then the probability being 1/2 just makes total sense intuitively. So um, now the probability of red, given that it's a heart, is slightly different, right? The difference here is after we've drawn a heart, we know all the hearts are red cards, right? So it's 100% a red card as soon as I know it's a heart. And again, that's different than the probability of red. You notice that the probability of H given R is different than the probability of H, 1/4 versus 1/2. And the probability of red given H compared to the probability of red is different, right? So these are not independent sets. We can still calculate the conditional probabilities, but they are not independent sets. All right. And then taking a look at example 2, we have the set of integers 1 through 40 inclusive. Okay, so inclusive means it includes the endpoints. If you say between 1 and 40, some people think that's from 2 to 39. And I can see that argument. That's not a bad argument. But mathematicians use this word inclusive after the range of values when they mean for the endpoints to be included. All right, and so we have this set. And we have the set F. If it's divisible by 5, it's in set F. If it's divisible by 3, it's in set R. And T is the set of all values that are divisible by 2. And then we're asked to find these three probabilities. And the first one, part A, I really went to some trouble to try to make sure that we had good information. So I listed the entire sets, right? So the set F are the values 5, 10, 15, 20, 25, 30, 35, and 40. And this is true in discrete probability. If the event sets we're looking at are reasonably small in terms of cardinality, we can just list everything in them. This is actually a good technique, right? And then R, we're listing everything that's in R, 3, 6, 9, and so on. Okay, and you just can count the figures, right? So, when you're counting up, you're like, oh, there's 1, 2, 3, 4, 5, 6, 7, 8. 8 over 40 is 1/5. So that's what we're doing here. Same for the set R. Okay, and then by inspection, what do I mean by inspection? Well, if we're looking at the intersection, right, we're saying, look, what numbers can I find in both sets? Well, 15 is in both sets, right? And 30 is in both sets. Is there anything else that is in both sets? No, no, it's just 15 and 30, so that's 2 over 40, which reduces to 1/20th, right? Okay, so again, this is another reason that it's good, if we can, to just enumerate or list all of the outcomes, right? It makes figuring out these probabilities quite straightforward. And then we put it into the conditional probability formula, right? So the probability of F intersect R, right? That's the 1/20th. That's in the numerator. And then the 13/40ths comes from the probability of R in the denominator, right? And then when we invert and multiply, the 40 and the 20 cancel, giving us 2. So we have 2/13. Okay? So just trying to make sure you understand how to use the formula. Um, there sometimes are ways to shortcut these conditional probability problems, but we can always use the formula to find the right answer. And one thing I finally did was I was like, look, if I just had all these probabilities, then I could use the formula really quickly, right? So the fives, which makes sense, 1/5 of these integers are divisible by 5. The three's a little different. Why? Because it was 40, and so we had 39. We have a little more than 1/3, right? 40 is not divisible by 3. So actually, we have a little less than 1/3, right? 3 times 13 would be 39. But we have about 1/3 of the integers between 1 and 40 that are divisible by 3, which makes sense, and half of them are divisible by 2. And then if you list out those sets and count them up, or if you count them up in your head, you quickly arrive at the probabilities for those intersections. Okay, then for 2b, the probability of t given r, right? So I need t and r, which is the 3/20ths, which goes in the numerator, right? Divided by the probability of r, which is 13/40ths, which goes in the denominator. Invert and multiply, do some canceling, and that is 6/13ths, which makes sense. If it's divisible by, well, 2, right? Half of the set of R should be divisible by 2, about approximately half. And we get approximately half, not exactly half, but again, there are 13 values in the set R. Okay, so those were pretty straightforward once we had those probabilities. And then for 2C, the probability of F given T, again, the probability of F intersect T, you can see the second from the bottom on the left is 1/10. The probability of T is 1/2. So I'm multiplying 1/10 times 2 over 1. The 2 and the 10 cancel, and I have 1/5. All right, so those are the ways that we do these um, calculations. And let's jump to our conditional probability notebook, and you can see that we have some of the same things. I'm going to see if I can fix this. Um, okay. And I did example 1 and I did examples 2, A, B, and C already. But we have these additional practice problems. And suppose that in Lincoln County, 54% of households have a dog. Okay, so the probability of D, sorry, is equal to, actually, let me do it this way. Let me do prob underscore D equals 0.54. Okay, why? Well, because when I enter that, right, it assigns that. So I'll have this variable I can use. I also want to do, right, the probability of, I'm going to call it prob C, the ones that have a dog and a cat, right, and that's 0.27. Oh, wait, no, I'm going to have to do I'll do it D and C. Why D and C? Well, because it's D intersect C that they've given us, right? So we have prob D and prob D and C. And again, when we evaluate it, you can see that both of these variables have been assigned properly. And why am I doing that? Well, because the probability of, okay, so if you randomly select a household that has a dog, what is the probability that it also has a cat? So this is, wait, this is the probability of C given, wait, sorry, right? Yeah. The probability that if you randomly select a house that has a dog, so that's the given. The dog has already been selected. What is the probability that it also has a cat? Well, it's going to be the probability of D and C divided by the probability of D. And sadly, I assigned that variable but didn't evaluate that variable. And this makes sense. Why? Because 27 is half of 54. And if 54% of the houses have a dog, but 27% have a dog and a cat, that's half of the 54 houses, 27 houses have a dog and a cat. So this value makes plenty of sense. Okay? And doing the same thing, suppose that in Washington County, 51% of households, let me do that all lowercase, prob, have central air conditioning, so that equals, oops, sorry, 0.51, right? And then prob underscore C. We have that variable assigned. And then I'm going to do prob. What are we doing? We're doing F and C. And what's that equal to? That's equal to 27%. Sorry, 0.27. And showing what that's equal to. All right, so we have these variables assigned. And then we're doing the same thing we did up here, right? We're doing the probability of, let's see, if you select a central air conditioning house, okay, so that's the probability of F given C, all right, which is the probability of F intersect C, right, divided by the probability of C. And so we get about 53%, which makes sense, right? We know that 27 is half of 54, so it's a little less than half of, excuse me, it's a little more, 27 is a little more than half of 51, which is smaller than 54. So yes, this value makes sense. And lastly, we have that Andrea is a very good student, or Andre, whether it's a male or female version of that name. Andrea is a very good student. The probability that she studies and passes her mathematics test is 17 out of 20. If the probability that Andrea studies is 15/16, find the probability that she passes her mathematics test, given that she has studied. Okay, so the probability of studying equals 15 divided by 16. Okay, so 93.75% of the time she studies. The probability that S and P that she studies and passes is 17 out of 20. All right, there are the two variables that we need. And then the probability that she, probability of P given S is going to be equal to what? It's going to be equal to the probability of S intersect P divided by the probability of S. Um, Notation wise, we usually write this backwards so that I'm dividing by the thing that's on the right, not by the thing that's on the left. Intersections are commutative though, so that's not a problem. And we find the probability is just less than 91%. Okay, so again, I tried to show this in terms of the variables so you could see the formula being implemented. And that's all that we have with conditional probability. I'll see you next week with the next installment of the probability units for this course. Have a great day.